Hey there, welcome back to our course on advanced quantum mechanics. This is lecture 32. Remember, we considered changing Heisenberg cuts. So we had a system A and then some system B, and system B could, for example, be a measurement apparatus that measures something about system A. And then the new Heisenberg cut that we were considering is the full system AB. Now, what are the states? We assumed here that the big system is in a pure state. So rho hat AB is given by some state omega, that's a pure state. And then we saw that the density matrix of system A is rho hat A is obtained by taking the trace over system B of the density matrix of the full system, and the density matrix of system B is analogously obtained by taking the trace over system A of the density matrix of the full system. We say in this case that we trace out system B or we trace out system A. We saw that the more entangled the two systems are, that is to say, the more entangled the state omega is, the more mixed are the density matrices of system A and system B. And what do we mean by more mixed or more entangled? Well, we use for this purpose two different notions. We use the entanglement entropy entanglement entropy. The entanglement entropy of our system AB is by definition the von Neumann entropy of the density matrix of one of the subsystems, which is minus the trace of rho hat A logarithm rho hat A. And this is well defined because it turns out that it is the same as the entanglement entropy of rho hat B. So it doesn't matter from which subsystem we calculate it. It's always the same. And that's because the eigenvalues, the non-zero eigenvalues of rho hat A and rho hat B were the same, including degeneracies, and so the entanglement entropies came out the same. So rho hat B logarithm of rho hat B. Okay, so the entanglement entropy measures the mixedness of a subsystem, but as such, it's also measuring then the entropy, the entanglement entropy, or the amount of entanglement between system A and system B. And then secondly, we said, okay, the entanglement entropy is good and fine, but to calculate it, we need to actually take the logarithm of the density matrix, and that's a bit messy. In order to do that, we have to diagonalize the density matrix. So we said, okay, there's another measure that we can also use, and that's the purity of a state. And the purity is defined to be the trace of the square of the density matrix. And again, this purity measures how mixed subsystem A is, and therefore it measures how much subsystem A is entangled with subsystem B. And again, that notion made sense because it actually comes out the same if we calculate the purity of subsystem B. And that's, again, because the eigenvalues of these two density matrices are the same. Remember too that what I just said is true if the total system is in the pure state. That is to say, if B, as we say, purifies A and A purifies B, in the sense that if you consider them together, the total system AB is in a pure state. And remember, there's a dilation theorem that says that if you have any system in a mixed state, there always exists a B. In fact, there always exist infinitely many possible B's, such that A and B together are in a pure state. That's why we can, for practical purposes, always assume that we are in a pure state. That's not to say that experimenters can do that, but as a theoretician, you can do that. All right, so what's new? We saw all of this before. Now, what we are going to do today is study the time evolution of this. Study what happens if the two systems are interacting with each other, and therefore the states change over time, and therefore the mixedness, for example, and the amount of entanglement between A and B can change over time. In particular, this will allow us to cover the measurement process. Because the measurement process, where a system B is a measurement apparatus that acts on our system A of interest to perform a measurement. In the bigger Heisenberg cut of system AB, this is an interaction. The measurement is an interaction. So this thing could be a microscope with a computer and a printer that prints out the results of the measurement. It could be a huge system here, and that is our quantum system that we are interested in. And then the whole thing is it's a total quantum system. It's just a regular quantum system that is evolving according to the Schrödinger equation of the big system AB. Of course, system B could also be a tiny measurement apparatus. It could be as small as one particle, like one photon that scatters of A, or one electron that scatters of A. But it could also be a big thing. Doesn't really matter. So by studying today the general case of two quantum systems interacting with each other, we are including automatically the case where one quantum system performs a measurement on the other. And therefore, in particular, we are covering the case of what we used to see as a wave function collapse, as a state collapse, right? So system A, for example, would normally, if not interacted on by system B, system A would just evolve according to the Schrödinger equation on its own. And then if a measurement happens, if system B interacts with A, system B acquires some information about A, and then the state collapses. And if B, the measurement apparatus, is something that we don't have under control, for example, it might just be a stray electron coming from the environment that scatters of A, then the electron may measure some information about system A, but we will never obtain that information. So therefore the wave function collapse happens, but we don't know into which state. So therefore, and this is actually a very often occurring situation, therefore we have to describe this situation as system A evolving from a pure state, this pure state in which we may have prepared it, into a mixed state. Namely the mixed state after the wave function collapsed into one of possible states according to what the measurement outcome was and according to probabilities for the various measurement outcomes. So from the perspective of the small Heisenberg cut directly around A, what happens is that initially system A evolves freely and unitarily according to the Schrödinger equation. Then a measurement happens to it, and then it ends up in a mixed state. Now we have all the tools available to consider that same process from the perspective of the big system AB. And now we can start with the pure state of both systems together, both subsystems together. And then that pure state will evolve unitarily according to the Schrödinger equation of the big system. And there's not going to be any collapse ever. But we can calculate, that's what we will do today, how what looks like a wave function collapse, what looks like the pure state matrix of A, pure state density matrix of A, evolving into a mixed state density matrix. How that comes about. So that's what we will do today. We'll study the dynamics of composite systems. And we start with the simplest possible case. And the simplest possible case is, of course, the case where our two systems start out unentangled and then they just happen not to interact. So consider this case, simplest case. Here we have a system B and a system A. And of course, we are going to work with the big Heisenberg cut here, but system B just evolves, system A just evolves, and no interaction. We will just consider as a test run of our machinery the situation where the measurement apparatus isn't measuring A. It just doesn't do it. It's just not interacting with A at all. We simply have two systems that stay apart. They start out in an unentangled state completely independently, and then they stay this way. So this is the time axis here. Okay, so we work in the big Heisenberg cut. So we work with this picture, of course, right? So AB. Now, what happens in AB? In the system, for system AB, we have to ask, what's the initial state? What's the Hamiltonian? What's the time evolution? How does the state evolve? How about purity, mixedness, and entanglement as the time evolves? So we start out with the initial state. The initial state of the big system AB is omega t naught. It's some pure state. And let's say it is psi of t naught tensor phi of t naught. So it's an unentangled pure state. Unentangled pure state. Well, we know it's pure because we can write it simply as one vector and instead of a density matrix. And it's unentangled because it's a tensor product of two vectors here. So then we use the Schrödinger picture. Could use other pictures, but it doesn't really matter. Usually these studies are done in the Schrödinger picture. It's just much more convenient. In the Schrödinger picture, let's look at what the Hamiltonian is. Let's say the Hamiltonian, so I won't put a subscript S here for Schrödinger picture anymore. Let's just understand it's in the Schrödinger picture. In fact, for simplicity today, I will assume all the Hamiltonians not to have any extra time dependence, and therefore the Schrödinger Hamiltonian agrees with the Heisenberg Hamiltonian. So we use the Schrödinger picture, and we now need to write down what is the Hamiltonian of the total system here. Well, if the two systems A and B have nothing to do with each other, which is what we assume to start with in the simplest case, then the energy of the total system is the sum of the energies of the subsystems. And this means that the Hamiltonian is given by, and now we have to be careful, it's the Hamiltonian of subsystem A plus the Hamiltonian of subsystem B. But remember, they act on different Hilbert spaces. This operator acts on the Hilbert space of the total system. The Hamiltonian of subsystem A acts only on the Hamiltonian of its Hilbert space. Just a sec, I need to wire up the power supply. So this means that we have to put here a tensor. What is this? Oh, just a sec, I have to fix the software. All right, so we have to put here a tensor, the identity, and then one tensor, the Hamiltonian of subsystem B. Right. So this is the total Hamiltonian now. See, this operator is acting on the full Hilbert space of our composite system and that one as well. Now, this is the total Hamiltonian, and yes, they are all time independent. Now, this means that we can immediately write down what the time evolution operator is, namely u hat of t is equal to e to the power of t minus t naught divided by ih bar, and then the Hamiltonian of the system AB. Right, this time evolution operator obeys the equation of motion for time evolutions. Now, from that, we have that the time evolution of our operator, of our initial state is given by u hat of t acting on omega of t naught. So this is e to the power of t minus t naught divided by ih bar, and then h hat of system AB acting on psi of t naught tensor phi of t naught. This is an operator that acts on the entire Hilbert space, and the exponentiation of it is, and so all of this is acting on that, the Hilbert space in which this state lives. Now we can evaluate this a little bit further, namely explicitly. What does this mean for the subsystems? We've just solved the dynamics for the total system AB, but what does this mean for the subsystems A and subsystems B? Well, let's see. We have that u hat of t is equal to e to the power of t minus t naught over ih bar. And then let's spell out what the h hat of AB is. It is h hat A tensor 1 plus 1 tensor h hat B. Now, we have e to the power of something plus something. If these were numbers, then recall we would have e to the power of a plus b equal to e to the power a, e to the power b, if a and b behave just like numbers, which is to say, if there was no issue of non-commutativity, right? If a and b commute, then we can conclude that. That's just by working out what the power series is, write e to the power ab as the series. N equals 0 to infinity, and then 1 over n factorial, and then a plus b to the power n. When you work all of that out with the binomial theorem, you get this, right? So all of that works as long as a and b are commutative. Now, here we actually have that the two operators in question, namely this one and that one, they do behave just like a and b here. They do commute. Namely, we have that h hat A tensor the identity times 1 tensor h hat B minus, and then the other way around, identity tensor h hat B times h hat A tensor the identity. Well, what is this? Well, if you remember the axioms for tensor products of operators, you know that this is h hat A tensor h hat B, because you simply multiply the first element with the first element and then tensor it with the second element times the second element. So you get this. and then minus, and here the same, first element multiplied with the first element, that gives us an h hat a, tensor second element with second element, that's h hat b, and we see this is 0. Great, so these operators here commute. These are just numbers in front, they don't matter anyway. They don't contribute to any non-commutativity. So therefore, we can conclude that we can write the time evolution operator in our composite system. The total time evolution operator can be written as e to the power of this times e to the power of that. So it is e to the power of t minus t naught over I h bar, and then it's h hat a tensor 1 times e to the power of t minus t naught over I h bar, and then 1 tensor h hat b. Now, what can we do with this? It looks still a little bit messy. Again, let's do a side calculation. Or let's not recall, but let's say notice. Notice. What happens if we calculate, for example, h hat a tensor 1 and take the square of it? Well, here we don't have to take the square of it. We have to exponentiate it. But exponentiating an operator consists of taking all sorts of powers of it and then adding them up in the series, right? So in particular, the square will become important. Now, what is it? It's h hat a tensor 1 times h hat a tensor 1. And what is this? Remember, first times first, tensor second times second. This is h hat a squared tensor 1. Similarly, and so we have that h hat a tensor 1 to the power of whatever is equal to h hat a to the power of n tensor the identity. And therefore, we also have that e to the power of t minus t naught over I h bar. And then h hat a tensor the identity is equal to e to the power of t minus t naught over I h bar, and then h hat a, and down here tensor the identity. And the same is true, of course, for one tensor h hat b. And this means that we can now, that we have this here, we can, you see, we can take this expression and pull the tensor identity down. And here too, we can take that expression and this 1 of 1 times tensor, we can pull that down as well. So therefore, we obtain that u hat of t, the full time evolution operator, takes the form e to the power of t minus t naught over I h bar, and then h hat a tensor the identity times 1 tensor e to the power of t minus t naught over I h bar h hat b. Now, remember how multiplication works for tensor products, first with first, second with second. So therefore, we have that u hat of t is equal to this times that, so e to the power of t minus t naught over I h bar h hat a tensor second factor times second factor, that's e to the power of t minus t naught over I h bar h hat b. Now, that's great, because what we recognize here is that this would have been a time evolution operator that we calculate if we choose a Heisenberg cut just around system A. right? So this is time evolution operator for system A alone. So therefore, what we can, and similarly here, this one, and so therefore for system B alone, right? Okay, so from this, what we can conclude is that omega of t, the time evolved state of the total system with a big Heisenberg cut, which is u hat of t acting on u of t naught, is equal to e to the power of t minus t naught over I h bar h hat a. And tensor, the other one, t minus t naught divided by I h bar h hat b. And that acting on the initial state of the total system, which is psi of t naught tensor phi of t naught. Because remember, we started our dynamics by assuming that the two systems are in pure states. The total system is unentangled, right? That was our initial state here. And that's the time evolution of it. Now, remember how the tensor product works. If you have a tensor product of operators acting on a tensor product of vectors, then again, first acts on the first, second acts on the second. So therefore, we obtain that this is equal to e to the power of t minus t naught over I h bar h hat a acting on psi of t naught tensor, and then it's e to the power of t minus t naught over I h bar h hat b acting on phi of t naught. And remember that if we had not worked with the big Heisenberg cut, but instead we had just made the Heisenberg cut around system A, then if we had just time evolved, according to the Schrödinger equation, just with respect to the time evolution operator, with respect to the Hamiltonian h hat A, then this would have been the dynamics of that subsystem. So psi of t, it's this. And tensor phi of t. Okay, so what we see here is, therefore, we see that the state omega of t remains of the form vector tensor vector, not sum over vector tensor vector, but just vector tensor vector. So therefore, we see that omega of t remains a pure state under the time evolution. And that's something we would have expected. And each subsystem evolves according to its h hat a or h hat b and its Schrödinger equation, unitarily. Namely, we would have that psi of t is equal to trace over system B of omega of t. Not enough space to write this. Okay, so remember, if we wanted to do it the strict way from scratch, calculating everything from the big Heisenberg cut in which we are operating here, then we would have to calculate, let me put it this way, we would have that rho hat A of t is equal to, well, the trace over system B of the time-dependent state of the total system, right? And then you can show that this is ... maybe I'll leave it to you as an exercise, that this is then indeed psi of t, where psi of t is e t minus t naught over I h bar h hat a acting on psi of t naught. Okay, so everything is as we might have expected. If you move the Heisenberg cut to a larger chunk of the universe, then as long as the two subsystems involved are not interacting with each other, then each subsystem just evolves according to its Hamiltonian in a unitary fashion. Okay, but now imagine that we have an interaction going on here. So now let's upgrade this to the really interesting case. Now, assume that A and B can also interact. Well, how is that described? Well, in this case, the Hamiltonian, then the Hamiltonian of system AB is equal to, as before, having a contribution of the energy from system A and a contribution to the total energy from system B. But also, there's going to be some interaction energy, right? For example, if the two subsystems, let's say they are charged, and then let's say they have the same charge. So then if they approach each other, then you have that the potential energy goes up, right? If you press them closer together, then they have a high energy. Or if they have opposite charges, then you gain energy by bringing them closer. So this is where you would have potential energies that describe forces between the two subsystems. An example for this would be this. We will not be fixated on that example. It's really just to illustrate. So example, let's say we have two electrons. Then how does it look like? Well, we would have H hat A is, let's say, of the first electron, PA, vector hat squared divided by 2m. Just the kinetic energy of the first electron. Then we would have H hat B. That could be the kinetic energy, P vector hat squared over 2m, kinetic energy of the second electron. Let's call it B. And then what would be the interaction Hamiltonian between them? Well, H hat interaction could be, and at first I write it schematically, the way you would often see it abbreviated, but then just to make sure you're getting the full picture, I will also give you the details of it. So it's some alpha divided by square root of the difference in the position between the two electrons. So we have the position of electron A minus the position of electron B, and then we square that, And then we take the square root of that. That's the distance. So that's a 1 over r, or 1 over distance potential. And then it's positive in order to describe the situation where the two particles are repulsive. Two electrons, same charge. Now, what exactly does this mean, however? Now, to be completely strict about this, remember, here we need tensor identity. And here we need 1 tensor this. And where does this thing live? Well, strictly speaking, this is really alpha divided by, and then square root of, and then we have x vector a hat squared tensor the identity plus identity tensor, and then, oh, sorry, no, the square is not there yet. It's not there yet, right. And then here we have the x vector up, vector hat, and then b, and then we take that thing squared, right? So this is a vector with these components. We take this squared and then take the square root of that. And you may wonder, okay, now we have an operator in the denominator. How do we deal with this? Well, remember that when you have to take a function of an operator, then if the operator is self-adjoint, you can make use of the fact that it has an eigenbasis. And in the eigenbasis, you can take the function of the eigenvalues. In this sense, you can handle the Coulomb potential in quantum mechanics. All right, so now what is the time evolution? So this is just for illustration. Let's now come back to the general question, namely, what's a time evolution if you have a Hamiltonian for your big quantum system that has an interaction term? You see, it's wise not to put this thing in here, because otherwise we would have to write stuff all the time, complicated formulas, right? So let's just call it H interaction here for now. All right, so coming back to the big question, what is the time evolution? So now, time evolution now. Well, let's say we have, again, same initial state. Omega of T naught is an unentangled pure state. So it's just psi of T naught, tensor phi of T naught. We can write it down as just a vector, so it's pure. And it's unentangled because it's just one term of this tensor product, not the sum of those. So this is unentangled and pure. Unentangled and pure initial state. Then the time evolution operator is again obtained simply by exponentiating the Hamiltonian. T minus T naught divided by IH bar, and now you had of AB. And then we obtain our state of the big system, omega of T, is U hat of T acting on the initial state, omega of T naught. And explicitly, this is simply e to the power of T minus T naught divided by IH bar. And then, oh, did I write you? I wrote U hat up here. This is H hat. See, if this was a live lecture, one of you would have told me for sure. Probably all of you would have told me by now. All right. Okay, so right. So here we have H hat AB, and that's acting on the initial state, which is psi of T naught tensor phi of T naught. And it seems that so far so good, nothing really has changed. Just because we introduced an interaction Hamiltonian to the total Hamiltonian, we still calculate the total state as before. And in particular, we see ordinary, unitary time evolution according to the Schrödinger equation, because this state, right, this state solves the Schrödinger equation, solves IH bar d by dt, not psi, omega, omega of t equal to h hat ab, omega of t. So we have ordinary unitary time evolution according to the Schrödinger equation and no state collapse. All right. Now that's curious because what might happen here is actually this situation. Namely, let's say we have, let me change the color here. Let's say we have two electrons. So we have an electron and another electron, and initially they might be so far away that they evolve freely. The interaction Hamiltonian is there, but the electrons are so far away from each other that they don't repel each other significantly yet. And then they evolve, and they might have initial states such that they are on a collision course, right? And then our electrons evolve, and then they sort of meet, and they repulse each other, and then, yep, like this, right? So that would be schematically what is going on. So our electrons initially don't interact, but then they scatter off each other, and then they travel away, and then they don't interact later on. So what do we expect from the perspective of the small Heisenberg cut? If we do a Heisenberg cut just around system A, just around our first electron here, well, then we expect that it is evolving unitarily, happily, undisturbed, according to the Schrödinger equation, until electron B comes along from the environment, and it performs a measurement on our system. How? Well, because it's being repulsed, just because of the electrostatic repulsion. Namely, our electron B learns something about how fast our electron A is, or where it is. It will acquire some information on the basis of having scattered off our particle A, right? And that will lead to a state collapse for our system A, which is to say here, the state is pure, but then over here, it is mixed. And this is where the collapse happened. And you could flip the picture around and say, oh, it's system B we're interested in, and system A is the intruder, and it measures system B through the interaction. The whole thing is, of course, symmetric. And then we see that the density matrix of system B is pure until the interaction happens, and then it will be mixed. And before we learned how to handle Heisenberg cuts, that's where we had to leave it. But now we calculated the dynamics for the total system AB, and we found that the total system AB, is actually evolving completely unitarily, according to the Schrödinger equation. And we can calculate the omega of t, and it's as pure as it started. So that means we have, in fact, described in solving that, in solving the dynamics for system AB, we must have implicitly also solved for how this collapse happened. Let's see how that actually came about. Namely, let's work out exactly what the time evolution operator looks like. So our time evolution operator is now e to the power of t minus t naught over IH bar. So we try to do now the same thing as what we did before without the interaction Hamiltonian, right? So it is h hat A tensor identity plus identity tensor h hat B plus h hat interaction, where this operator acts on its own already on the full Hilbert space. So for example, this could be, for example, h hat interaction could be something like an operator A hat tensor an operator B hat. That would be a simple example of an interaction Hamiltonian. I just want to stress this so that you're not worried, where does this thing act? Well, it acts, you know, if it's, for example, of this form, it acts on the full Hilbert space. All right, so we have this. Now let's ask, does this thing factorize? So does it factorize again? Remember, we used before that e to the power a plus b is equal to e to the power a, e to the power b. That's what I mean by the factorization. That's true if the commutator between a and b is 0. Now, we have 3 terms up here, and those 2 commute, but this one is not going to commute with that one. See, now we have no, because the h hat A tensor, the identity operator, does not commute with h hat interaction. And similarly, h hat, no, sorry. One tensor h hat B with the interaction Hamiltonian also generally doesn't commute. Why is that? Well, let's remember what the interaction Hamiltonian could be in a reasonable situation, such as if there are 2 electrons that scatter off each other. Well, then we would have that the free Hamiltonians look like this, p squared over 2m, p squared over 2m, and then the interaction Hamiltonian is the difference between the locations, 1 over the distance between the locations. And the key thing here to notice is that these PA operators are not going to commute with these XA operators. And these PB operators are not going to commute with these XB operators. Therefore, they don't commute. These guys don't commute. See, this thing contains P hat B, and this thing contains x vector B hat. And so therefore, they don't commute, and the same is true up here. So therefore, we cannot use this. This does not work anymore if we have a non-trivial interaction Hamiltonian. So things don't factorize. And this has 2 consequences. The first consequence is we are pretty much stuck with this, and we cannot just solve it and say, okay, it's the time evolution of the first system times the time evolution of the second system, as we could before. It's just no longer possible. And therefore, we will have to do perturbation theory. And secondly, this will be the reason why in an interaction, entanglement is being created. And that's what we want to see now. So if the 2 systems, the 2 subsystems, interact with each other, then from the point of view of the big system, they become entangled. And that's the reason why, from the point of view of a small system, a Heisenberg cut around this one, the small system starts out pure, and then in the entanglement, and then in the interaction, the wave function collapses, the state becomes mixed. From the perspective of the bigger Heisenberg cut, this is simply saying that the total state starts out pure unentangled, and then becomes, it's always pure, of course, but it becomes an entangled state in the interaction. And then as we do the entanglement, as we get the entanglement, the subsystem states become mixed. All right, so let's see how that looks like explicitly. Well, explicitly, use perturbation theory. Now, quantum mechanical perturbation theory is a big topic, I will not go into this now, but I will just use a very trivial example of it that is immediately evident. Namely, what we need to calculate is u hat of t acting on the initial state, right? So we have omega of t is equal to u hat of t acting on, well, the initial state is, I could have written omega of t naught, but let's just spell it out. It's psi of t naught tensor phi of t naught. Right? We assume here that our two particles or two systems A and B start out independent. Each one is in its own pure state, psi 1 of t naught, the other one is phi of t naught, and the total state is therefore just psi of t naught, phi, tensor phi of t naught. And then we time evolve that. And as I said, the time evolution operator is a mess now because it contains non-commutative stuff in the exponent. So we can't easily work out what that is. But what we can do is remember that the exponentiation of the operator here is a series, right? The exponential is a series, the function of the exponential series. So this is really a series in powers of this operator here. And what we can do is we can say, well, for small time evolutions, for small times, if t is not much larger than t naught, if this is a small number there, then for short time evolutions, and they may in practice not even be very short, we can calculate what this is by just taking the first few terms of the exponential. So we can write this as equal to 1, that's the first term of the exponential, plus, t minus t naught over I h bar, and then h hat of A tensor 1 plus 1 tensor h hat of B plus h hat interaction. You see what I'm doing here? I'm saying that e to the power of lambda is equal to 1 plus lambda, and that's what I wrote down so far. You know, e to the power of the Hamiltonian here, e to the power of this is 1 plus this, lambda, this, plus 1/2 lambda squared plus dot dot dot. And now let's write down the plus lambda squared plus 1/2, and then this thing squared. So we have here t minus t naught divided by I h bar, and then we have to do this squared, and then we also have h hat A tensor identity plus 1 tensor h hat B plus h hat int squared plus dot dot dot. So this is how the time evolution starts out. I'm not yet done because I'm only expanded Taylor expansion of the time evolution operator. We still have to apply all of this onto our state, namely psi of t naught tensor phi of t naught. Okay, And I guess you see how this works out, how you could actually, if you wanted to, and in practical applications, you may have to, actually work out what that is. So the first term would be, this is equal to 1 times the initial state. So it's psi of t naught tensor phi of t naught plus, and then we have t minus t naught divided by IH bar. And then you have this operator acting on that state. So you would have here H hat A acting on psi of t naught tensor, and then phi of t naught. And then you would also have this other thing here. You'd have plus t minus t naught IH bar, and then you would have psi of t naught tensor H hat B phi of t naught plus, and then you have, let's say this thing could be, for example, A hat tensor B hat, just to make it explicit so that we can spell this out now, plus t minus t naught over IH bar. And then you would have A hat acting on psi of t naught tensor B hat acting on psi of t naught. So now we're only done with the linear term, right? And then we would have plus 1/2. And then we get, we have to square this operator here and then apply that onto this vector here. So plus 1/2 dot, 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 lots of terms. A lot of practical quantum mechanical calculations consist of working out that sort of thing, hopefully with the help of a machine. Okay, so we know now how to calculate, in principle, what the time evolution is of the initial state. And one conclusion we can draw from this is that this, generally, this is not equal to some vector tensor some vector, right? It's not. Because it's the sum of lots of vectors, like this vector plus that vector plus that vector plus that vector, and plus a whole string of lots of vectors, and it's not of this form. Instead, what it is of the form of is like sum over j, and then you would have some vector j tensor vector, and also some label j here. So it's entangled. So what we see here is that the state omega of t becomes entangled because of the interaction Hamiltonian. When we did the calculation previously, without the interaction Hamiltonian, we also had an infinite sum of terms, but because of the factorization property, we deduced that actually all of this beautifully turns into just the tensor product of the two separate time evolutions of the two subsystems. But here, no such guarantee. And generally, what we have is that omega of t equal to u hat of t acting on psi of t naught tensor phi of t naught starts unentangled, but then becomes entangled. But becomes entangled. And we know from prior results And we know from the previous lecture therefore, the density matrix of subsystem A, which is equal to the trace over subsystem B of time-evolved state of the total system starts pure and becomes mixed. So overall, what we therefore have is this. Sketch the physics of this. Let's say we have that we have two systems, system B, system A. Remember, B could be a measurement apparatus for system A. And then they evolve. And at first, relatively freely. I should draw it a little bit differently. Let's say they evolve like this, and then they interact with each other, and then they evolve freely again. Similarly here, it evolves freely, and then it interacts with our system A, and so on. All right, so what we have is, as we said, a free evolution as long as the interaction Hamiltonian is negligible. For example, because they're so far away from each other that the 1 over distance term of the interaction Hamiltonian is very small. Then essentially we have the simplest case calculation that we had before, where the subsystems evolve unitarily, where it factorizes, where the total time evolution operator factorizes in the product of the time evolution operators of the subsystem. So therefore, if A and B start out in pure states, they will remain pure states. And so this is pure rho hat A. And here, rho hat B is also pure. And then here, the interaction happens. From one perspective, we can say it's a measurement, and therefore there's a collapse. So we could say measurement and collapse. That's from the small Heisenberg cut perspective. But also we can say it's simply interaction according to some interaction Hamiltonian. This is big Heisenberg cut perspective. And then over here we have that we have a mixed rho hat B, and here we have a mixed rho hat A. And we have that for the total system, we have that in here, omega of t is unentangled, and then here becomes entangled. And here we have that omega of t is entangled. We can calculate how much. And then if we do that, we can plot that. Now, of course, that depends on the exact system that we do, on exactly what system A, what system B is, what initial states they are in, etc., and what the interaction Hamiltonian and free Hamiltonians are. But schematically, what we have is, this. If this is the time axis, we can plot here, for example, the entanglement entropy. of system rho A. Remember, it is the same as the entanglement entropy or the von Neumann entropy of system B. What is it? Well, initially, we start with the systems unentangled. So there's no entanglement entropy. The two subsystems are pure. So we start with zero entanglement entropy, and it goes like this until the interaction kicks in. And as the interaction kicks in, the entanglement entropy increases, and then the entanglement entropy plateaus out as the interaction ceases, and the two subsystems are again no longer in contact with each other, for example, because they are sufficiently far apart from each other. Similarly, we can also plot the purity. So we could also plot here time axis, and then what about the purity? Here we have the purity of rho hat A, which is the purity of rho hat B. And what is it? Well, it starts out with 1, right? Because purity 1 means the state is pure. And then when the purity drops, that's when the state becomes mixed. So we have the purity stays at 1 until the interaction kicks in, and then it diminishes, and then again it stays relatively constant. Those waves are not intended, right? It's a plateau, and then it drops during the interaction, it becomes a mixed state, and then it stays straight over here. Right, so that's the overall picture that we obtain here. Now from this, you may take away the message that interactions mean measurements and measurements mean interactions, and you may take away that whenever two quantum systems interact with each other, especially if they interact strongly with each other, then each subsystem will not evolve unitarily anymore, but instead it will incur a collapse. And if we want to do things with the Schrödinger equation, we really really need to have the bigger Heisenberg cut that has both of them, that has both subsystems included. Now, that's sort of correct, but there is a very important set of exceptions, or approximate exceptions. And that works like this. Let's ask, can interactions also be non or almost non-entangling? You may wonder, what? No chance, right? Because we are generating with an interaction so many terms that entanglement is sort of programmed into it, right? I mean, how could it be that all these many terms that we get from the interaction Hamiltonian being exponentiated together with the free Hamiltonians, how could we possibly not have entanglement? But it turns out it is super important that, because it just occurs all over the place, that interactions are strong without being entangling. So yes, this can happen. And here's how. Assume that, again, the initial state of our system is psi of T naught, tensor phi of T naught. And assume that the interaction Hamiltonian is, let's say, a tensor B, just to make things a little bit more concrete. And that sort of thing happens often, that the interaction Hamiltonian takes this form. It could also be the sum of terms like this, but for our purposes now, let's just assume it's just one of those terms. And assume one more thing, which is that B hat, when acting on that state here, remember it acts on that Hilbert space, it acts on the Hilbert space of system B, phi of T naught, is actually, it turns out to be an eigen, that the phi of T naught is an eigenvector of B. So let's assume this to be the case. And I will later explain when and why that sort of thing occurs. So assume that the initial state of one of the two systems, let's say system B, is an eigenstate to its part of the interaction Hamiltonian. When that happens, then something special happens in the time evolution operator. Namely then, in the Hamiltonian H hat AB, which is equal to, if you remember, H hat A tensor 1 plus 1 tensor H hat B plus now A tensor B when this Hamiltonian, when it acts on our initial state, and it has to, in fact, powers of it have to act on our state here, then what happens? Then in this state, we have that H hat AB, or the word in, I should write here for this Hamiltonian, we have that when we act with it on our omega of T naught, then we can write it as H hat A tensor 1 plus 1 tensor H hat B plus A hat tensor, well, in principle, there ought to be a B operator acting on, psi of T naught, tensor phi of T naught. But because we have this, we can write here simply lambda times the identity. Right? And what that means is that this operator combines with that operator here. And so what we have is that this gives us H hat A plus lambda A hat tensor the identity plus identity tensor H hat B acting on psi of T naught tensor phi of T naught. And so this then behaves like some H hat tilde A tensor 1 plus 1 tensor H hat B, where H hat tilde is simply this here, right? This is H tilde hat A, i.e. Free evolution, by free I mean non-interacting, and so non-entangling evolution. according to our calculations before, where we didn't have an interaction Hamiltonian, because we just had a free Hamiltonian here, tensor 1 plus 1 tensor free Hamiltonian. It's a little bit more subtle, because we may have to worry about whether or to what extent the H hat B commute with the B. But I will neglect that for now. In fact, there is one more approximation that's getting into this. And the approximation is that this condition here, namely that the state is an eigenstate of its part of the interaction Hamiltonian, may only be approximately obeyed. But these approximations that I'm talking about here can be very good, in fact, excellent approximations. Now, let me show you why all of this is super important. So where does it occur? Well, everywhere. And what I mean by that is, it's the exception that it doesn't occur in the following sense. Consider, for example, a system A, which might be, let's say, an electron. And let's assume our system B is the, let me put it here, it's the, all of this needs more space. All right, so our system E, our first system is an electron, and the second system is the electromagnetic field. And this is system A, just one electron, and this is system B, that's the electromagnetic field. Electromagnetic field is a quantum mechanical system. We haven't really covered it in any detail, but it's a quantum mechanical system. And then we can look at the combination of two of them. That's the kind of thing we need to do if we want to study the interaction between light and matter. Or electromagnetic fields and matter. But how do we usually do it? Usually, and by usually I mean in a first course on quantum mechanics, we would write down something like this: IH bar d by dt, and then psi of x and t in the position representation is equal to everything in the position representation, so it's minus h bar squared over 2m, and then it's the Laplacian, and then that's the kinetic term, the p squared over 2m, and then we would write down plus something like E electric field of x times the position operator vector field, a position operator vector, and then maybe plus some magnetic field potential dot, as a dot here, and then p vector hat. And here, these guys are usually treated classically. Classical EM fields. Right? That's usually what one would do. All of this, we need to multiply with like this. They need to act on psi of x and t. Right? So that would be the usual Schrödinger equation, something like that, where we would have an interaction between an electron and an electromagnetic field. But why is that legal? Why would that be correct? Let's think about it. The electron is interacting with, let's say, a magnetic field. The electron is strongly interacting with a magnetic field. If you remember, an electron will spin around the magnetic field lines. So it's definitely not a small interaction, it's a strong interaction. Or let's say the electron is attracted by some, it's accelerated because of some electric field. Again, the electron is accelerated very fast. In fact, within a fraction of a second, you can accelerate an electron to almost the speed of light. So the interaction between an electron and an ambient electromagnetic field can be very strong. Why doesn't it make the electron's state become mixed? After all, the electron interacts with the electromagnetic field strongly. The electromagnetic field is a quantum system. The electron is a quantum system. The two systems interact, obviously, and very strongly. Why is it we can write down a Schrödinger equation for the electron alone? Shouldn't it be permanently measured by the electromagnetic field? Shouldn't there all the time be wave function collapses for the electron so that its pure state becomes a mixed state because it's interacting with the electromagnetic field? Why is this legal? Why legal? Shouldn't it be non-unitary? Shouldn't the evolution be non-unitary? Given the strong interaction? And the answer is no, because it's approximately okay, because the electromagnetic field is very often in a coherent state. And this is because of the way that charges and currents are generating electromagnetic fields. So very often the electromagnetic field is in a coherent state, which is approximately a eigenstate of the E operators and the A operators. See, the E and the A are really operator valued fields because these are quantum systems. But if the state of the electromagnetic field is in an approximate eigenstate of the electric and the magnetic field operators, then what we just calculated applies. An entanglement is not being generated. And this is such a good approximation that it's often not even mentioned in first courses in quantum mechanics that the Schrödinger equation with an electromagnetic potential in it is an approximation. Because ultimately we have the description here of two quantum systems that interact with each other, and we have to explain why they don't get entangled in spite of the fact that they are strongly interacting with each other. So what I wanted to convey here is that yes, every measurement is an interaction, every interaction is a measurement in principle, but there are exceptions. There are exceptional cases where you could even have a strong interaction that means a very weak measurement, or you could have a strong measurement that means a little bit only of an interaction. All those things can happen. And you may wonder, well, what if I want to know more about the situation when the electromagnetic field is not just in a coherent state? What if the electromagnetic field is not in an eigenstate of the electric, or not even approximately in an eigenstate of the electric and magnetic field operators? Then obviously the electron would get entangled with the electromagnetic field. And in fact, lots of very interesting things happen then. And in principle, this is a topic of quantum field theory, C, quantum field theory, but also for practical purposes, where the quantum field theory is usually tested in accelerator physics, but also practical technology is being developed with so-called non-classical light. Electromagnetic fields that are not in coherent states, that will get entangled with matter as they interact. And for this, if you want to know more about this, check out quantum optics. This super cool field where super cool experiments can be done, and already technologies are being developed, for example, for quantum cryptography and also for quantum computing. Right, let me close with a few comments regarding quantum computing. So in quantum computing, this study that we did today is at the heart of the technological realizations of quantum computing. And the reason is that in quantum computing, we try to harness the power of quantum evolution. And quantum evolution is the evolution according to the Schrödinger equation unitarily. And whenever our quantum processor, be it superconducting qubits or photons or be it ions, whatever physical system it is, whenever it is being disturbed by an intruder that comes in from the outside, and a stray electron, a stray photon, any other little system could come in from the side and interact with our quantum system, and then its evolution is no longer unitary. A pure state becomes a mixed state, right? Today we saw how that happens from the perspective of the big system. We can calculate these things. Anyways, for quantum computing, the technological challenge is that on one hand, we want quantum systems to evolve as undisturbed as possible. It's a bit like a lecturer doesn't want to be disturbed by his twin brother showing up and disturbing him while lecturing. Similarly, a quantum system is supposed to evolve just on its own according to the Schrödinger equation without being interfered by with some systems that come in from the environment. But on the other hand, we also want our quantum systems to be reactive, namely for the actual purpose of performing gate operations that do calculations. We need that the quantum systems can interact with each other. And you see, this is the central challenge, in my view, of building big quantum computers. The challenge is that on one hand, the quantum system that performs the calculation for us needs to be undisturbed. It needs to be as little prone to interacting with other things as possible. But on the other hand, its parts need to be able to interact with each other strongly in order to perform calculations. And this probably means that we need to learn how to transform quantum information that's encoded in one shape into quantum information that's encoded in another shape. For example, photons. Photons are not so prone to be affected by other systems. Photons can travel very far, very quickly, can communicate quantum information, for example, in their polarization, very reliably, without being impacted by the environment. However, photons don't want to interact with each other. It's very hard to make photons do calculations by having them interact with each other. You know, when you take two torches or two laser beams and have them cross each other, the photons generally don't interact with each other. If, on the other hand, you took something very reactive, such as ions, well, ions definitely want to react with each other, and so therefore they are great for performing calculations, but ions are also very reactive with the environment. So you see that the struggle is that on one hand, we want the quantum information encoded in physical systems that are not prone to interacting with the environment, but they must like to interact with each other. And I suppose technologically that's the challenge. We need to learn to transform quantum information from one shape, such as in the form of photons, where they're not prone to being interacted upon, to other forms, such as in ions or in superconducting currents, where we can make them perform interactions. In any case, for all these practical challenges of quantum technologies, the calculations that we did today are super important. And if you want to read more about it, you can look up the keywords, the keyword of decoherence. Decoherence happens when a system is interacted upon by its environment in such a way that its pure state turns into a mixed state. All right, so this is as far as we got today.